Okay, while people file in, I'm going to start with a couple announcements relevant to next week. All right, so next week we have on Thursday, February 16th, there won't be any office hours that day, and I'll get into why in a second. And then on the 17th, that's going to be our first exam review. But because of some conflicts I'm working around, we're going to end up doing it on Microsoft Teams, which is not my preference, but I just don't think that trying to hold an in-person review is going to be feasible that day or not the best solution. So that's not going to be ideal, but it'll be the best we can do for this first one. So I'll send out information about that via email. We do have a Microsoft Teams group for this class, even though we haven't really used it yet. So I'll send the invitation through that, but I'll also probably send it separately to make sure everybody gets it. In terms of the timing for that, this is the part that kind of sucks for you guys, but it's probably going to start between the normal start time for an exam review would be 2 p.m., but it might start later. So what I'm going to do is that day, 15 minutes before I get on Teams and start, I'll send out a mass email. So you have to kind of pay attention to that. I apologize for that. It's not the best situation, but I probably owe you guys an explanation for why the beginning of the semester is so screwed up. So I don't know if you all realize, but my job here is 30% teaching and 60% research. So I have to juggle those two things. Usually I can try to keep them separate from each other, but this semester, because of things beyond my control, I've had a lot of research-related commitments at the beginning that have conflicted. So the exam review Thursday and Friday, the reason for the changes next week is I have all-day meetings with the National Science Foundation. They're virtual meetings, so I'll be here. So what I'm going to do in class on Thursday, I'll be here, but it's going to deliberately be a little bit shorter than normal class, probably an hour or less instead of an hour and 20 like we normally do. We are a little bit ahead, and I did that on purpose by skipping some of the stuff at the first lecture that's, all the syllabus nonsense. So we, purposely have been a little bit ahead. So on Thursday, we'll kind of get back on track with a little bit shorter class. And then Friday, I don't know what time the meetings are going to end. They're all day, but usually they end a little bit early on Friday. No later than 4 p.m., but probably more like 2 to 3 p.m. So since the start time is undefined, and since I don't know if I'll have the classroom long enough to start the exam review late in person, and because I don't want you guys waiting around for an in-person session that has no defined start time, I decided to just do it on Microsoft Teams this time. So the good news is we're getting close to the end of all this nonsense. So I'll have one more week in March, right before spring break. That's a little bit screwed up. But then after spring break, when we still have 3 out of our 4 exams and all that stuff, I'll be all yours. So this is only a temporary thing. It's not going to be all semester like this, but just the beginning got a little bit messed up. So I apologize for that. For some reason, my whole tablet logged out. All right, let me make sure that the video is still going. It looks like it is. I'm not sure what happened there. Hopefully we can get through today's class without any problems. All right, so we're going to go into today's material. So what we're going to do today is actually finish Chapter 3, which is the end of the Exam 1 material, and I'll let you know clearly where that happens, and start on the Chapter 4 stuff, which will not be covered until the second exam. All right, I think these tables are accurate, but anyway, what we're going to cover today is nomenclature. So how do we tell the name of a compound from its formula or vice versa? Some people think nomenclature is kind of dumb, but it is important. If I sort of view this class as the beginning of your journey to becoming world famous chemists, and if you're going to do that, you have to know the language. So that's kind of what we're doing today, is teaching you some of the language of chemistry. And there are some tables in the book in this chapter that cover some aspects of nomenclature, which I'll cover a lot of those things today, but it'll be good to reference those tables as you're learning this on your own. So the first one we'll start with is ionic compounds, the first class of compounds we'll start with. And these are fairly straightforward. So the nice thing about ionic compounds is and this is the important distinction between ionic and covalent, which we'll cover later, there's no prefixes needed for ionic nomenclature. And so what that means is, as you'll see, you just need to name the two elements that are involved, do it in the right order, and you sometimes change the ending a little bit, but you don't have to put any prefixes before the element names like we will for covalent compounds. So that distinction will be more clear once we cover covalent, but that's the key thing here. So when you're naming an ionic compound, or when you're writing the formula, these sort of ordering applies as well. You typically will, or not typically, always will say the metal first. And we've talked a little bit about ionic bonding and the formulas of ionic compounds already, so you remember that the metal is the part of the ionic compound that forms the cation, comes from the left side of the periodic table. And then you're going to do whatever the nonmetal is second. So we're only going to cover what are called binary ionic compounds, which are ionic compounds that have one cation and one anion in the formula. Sometimes more than one of each to balance the charge, but only, one identity is only going to be one. And this order, as I said, applies to the formula and the name. So when you're writing the formulas for ionic compounds, you do it in this order, and when you're naming them, you do it in this order as well. So the cation part of the formula, as we said, comes from the metal that's in the formula. An ionic compound always contains a metal and a nonmetal, or a binary one would have that. And so for the first part of the name, you just take the name of the metal by itself. You don't have to modify that first part. You just name the metal. So if your ionic compound has sodium plus in the formula, you just call that part of the name sodium. You don't change it from sodium. Or if it's, calcium Ca2 plus, you just call it calcium. You don't have to put any sort of modifier on that for that part of the name. For the anion, you do something a little bit different. So the anion comes from the nonmetal that's in the formula, and you'll take the root name of that anion, so that's going to be essentially the element name, the beginning of the element name, but you're going to change the ending to IDE. All right, so if you had F minus in the formula, F is fluorine as an element, but when it's part of an ionic compound, we call it fluoride. Or O2 minus comes from oxygen, which is the element, but as an anion, we call it oxide. And then N3 minus, as an example, is nitrogen, but as the anion, it would be named as nitride. So we talked earlier about how to predict the charges of cations and anions. So that's going to be important, especially for building up the formula of an ionic compound. When you name it, whatever the charge of the anion is for that specific stable anion, you just use the IDE ending. Now, in the formula, you still have subscripts involved to tell you how many of each cation and anion there are. This we already talked about a while ago, if you remember, when we first introduced ionic bonding. And as a reminder, when you're doing subscripts for ionic compounds, you always use the lowest whole number ratio. So we have to figure out the charge of the cation and the anion and arrange or use the right number of them such that the positive and negative charges balance each other or cancel each other out. So use the lowest whole number ratio that allows you to do that. So that's something we covered a little bit earlier. We will review it a little bit today. But the formulas of ionic compounds is something that we already dealt with. So we're going to go through just a few examples of what are called binary ionic compounds, which have, again, just two elements in the formula, a metal and a nonmetal. So if we have MgCl2, now in reality you don't necessarily have to figure out the charges of the cations and the anions if you're given the formula. That's kind of already built in. If we go to the periodic table, though, we could easily predict that Mg is here in the second column, so it's going to form a 2 plus cation, and then chlorine over here in group 7 will form a 1 minus anion. It needs to gain 1 electron to get to the noble gas. So plus 2 cation, 1 minus anion. Again, for compounds that involve the main group metals, these first two columns here, you don't even really need to think about that when you're formulating the name, because this column is always plus 1, this column is always plus 2. Whatever anion is with has its own charge, but you don't have to think about the charges to put the name together, because it's just the names of the two elements that you care about. So that's a little bit of an extra information, but what we would have in magnesium chloride, just to sort of review and remind ourselves, is that it's Mg2 plus with 2 Cl minuses, but the way that we name that, we don't really care what the charges are. It's just going to be the name of the metal first, which is magnesium. And then for the nonmetal chlorine, we just change the ending to IDE. So this would simply be magnesium chloride. We don't have to do anything to indicate the ratios of the cations and anions or their charges, because for those main group elements, the charge is always well defined based on its location in the periodic table, and the formula tells you how to balance them, but you don't need to indicate that in the name. Okay? If we had CS2O, so this symbol is not one you should know off the top of your head because it's too far down the periodic table, but CS is cesium, so I probably should have given you a little bit of a hint about that one. But anyway, we have CS plus, which is cesium, 2 of those, and oxygen, to remind ourselves, so CS is here, it's in the first column, so it's going to be +1. Oxygen's over here, it needs to gain 2 electrons, so it's going to be -2 to get to the noble gas configuration. And so those are the charges, but again, we don't really care about that too much when we have main group binary ionic compounds. We just have to name the two. Cesium is the metal, which that one's too far down in the periodic table, so if you don't know that, that's okay. And then oxygen would change to oxide. Now, the other way that we could do this in homework assignments and tests is not give you the formula or the name or vice versa, but actually have you sort of produce both of them. So here we just have an example of give the name and the formula for the ionic compound formed from, all right, so strontium we should have given you the symbol for. I keep forgetting to do this. You guys are only responsible for the first 36 elements in terms of names and symbols. So anything beyond that, we'll give you the hint on the exam if you need to look it up what it is. We'll either give you the symbol directly or make sure you have that information in some way. So strontium is SR, that should have been given to you, and then iodine is I. It's also too far down, so both of these are, but that one you probably already know. So those are the two elements we're looking at. So if we want to find the formula, we do need to predict the charges of the ions first, and that comes from their location on the periodic table. So going back again to the periodic table, SR is here. It's number 38, so it's past 36, so you don't need to know the name of that one connected to a symbol. But if we gave you the symbol, you'd find it here, and it's in the second column of the periodic table, so it would form a +2 cation. All of these ones would form +2. Iodine is in the halogen group. It's the heaviest one that's not radioactive, and it's going to form a 1- anion to gain that 1 electron to get to the noble gas configuration. So those are the two charges, +2 and -1. And then what you can do is, just as we said, if you want to do this really blindly and without much thought, you just take the charges and cross them over to make them subscripts. So the strontium has a 1, which means you don't write a subscript, and then you have 2 iodines to balance the charge. 1 + 2 cation, 2 - 1 anions cancel out. So that's the formula. And then the name is just the name of the two elements. Again, no prefixes or suffixes needed for these simple binary ionic compounds. Strontium is the metal, and then instead of iodine, we write it as iodide. Okay? So that's the name and formula for that one. Sodium and sulfur, these ones we should know based on their location on the periodic table. So sodium is Na, sulfur is S. We need to find those two. So this is quite simple. This is a very similar one. So Na is here, number 11. It's in the first column of the periodic table, so we would predict it forms a +1 cation to get to the noble gas configuration. So sodium +1. The other element is sulfur, which is here, number 16. It's in the second or third to last column, so 1, 2 gains 2 electrons to get to noble gas, so we'd expect it to form a -2 anion. So a +1 cation with a -2 anion. We just, again, cross those charges to make them subscripts, make sure that the charges balance out. So that gives us Na2S, 2 sodium +1s to balance the 1 sulfur 2-, and the name is just the two elements with the IDE ending of the second one, sodium, and then instead of sulfide, it becomes sulfide. Sulfurs, it becomes sulfide. All right, so that's how we do binary ionic compounds involving the main group metals. Those first two columns of the periodic table in particular, you don't have to indicate anything about the charge. It's always going to be predictable and straightforward. So any questions on that so far? All right, the ones that are slightly more complicated are ionic compounds that involve transition metals. So remember that the transition metals are that middle part of the periodic table, the 3D, 4D, 5D blocks. Just I'll point it out quickly here. All these metals here And then some of the main group metals also, like indium, thallium, lead. Those are all main group metals as well in the P block. So those three, indium, thallium, and then tin and lead. And the issue with those metals, in most of the transition metals and these four main group metals, is the charge on the cation is variable. So it doesn't always form the same exact charge. It's not really predictable from the periodic table either necessarily. And so what that means is when you're naming compounds with these metals involved, you have to specify the charge of the metal in the formula. Because if you don't specify the charge of the metal, then the formula that would come from that name is ambiguous. Because depending on what the charge of the metal is, you're going to have different formula to balance the charges. And so you need to have that in the name. So the rules are very similar. There's only one difference that I'll show you. The formulas, use the exact same convention: metal first, then non-metal, or cation, then anion. So we don't change the order of anything in the formula, and the order is also the same in the name. All right, so the only difference is that in the name of an ionic compound that involves most transition metals as well as these four, you need a Roman numeral in parentheses after the metal's name to indicate what its charge is. All right, the charge again is variable for most of these, and so you put a Roman numeral in parentheses after the metal name. There's probably like 2 exceptions to the transition metals that you should be familiar with. So I don't think it's going to come up too much, but silver is always silver plus, zinc is always zinc 2 plus. Probably should know those two. In those cases, you don't really need the parentheses to indicate the charge. It wouldn't be wrong to do it, I would say. It's just extra information because silver is always +1, zinc's always +2. But for the rest of the transition metals, you definitely need this to indicate the charge. So if you figure out from the formula of the compound that you have, for example, iron 3 plus, Fe3 plus in the formula, you would write that in the name as iron with a Roman numeral 3 after it. So that tells you from the name of the compound that that's the charge on the metal, which for iron could be also +2. So if you had iron 2 plus instead in the compound, both of these are common charges for iron, you would write that as iron with a 2 in Roman numerals. Okay, so that's going to be, the big difference with transition metals is putting that charge in parentheses after only the metal name. The anions that we're dealing with don't have variable charges, so you only have to do it for the metal, but that indicates what the charge of that would be. And again, the reason for this is if we just wrote iron chloride, we wouldn't know if the formula of that compound is FeCl2 or FeCl3, but the number in parentheses tells us then which formula would correspond to that. So that's why it's important to be able to, unambiguously identify what compound we're talking about. Now this part here, you're not going to really be responsible for it, but again, since we're trying to teach you the language of chemistry today, I just want to go over it really quickly, which is some of these have common names as well. So when you have transition metals that have 2 possible charges, the one with the higher charge would typically have in the common name an IC suffix. So this naming convention is sort of old school, but you might see it from time to time depending on what source you're looking at, so I just want to make sure you're aware of it, even though we're not going to really test you on it. So if you had Fe3 plus in the formula, you could write it as iron 3. That's the way that we'll expect you to know it. But you might also see it as ferric. Fer comes from the Latin root for iron, so I guess even more confusing. But the IC ending tells you that it's iron 3. And then if you had the lower charge of that particular metal, depending on what the 2 charges are, would get the OUS suffix. So if you had iron 2 plus in the formula, it could be named also as ferrous. So if you see those IC or OUS names after metals, that also indicates their charge in some ways, but you need a little bit more context to know exactly what the charge is, unfortunately. So now that you know this, now that you know that iron 2 plus can be written as ferrous, you could tell me what the inorganic chemist's favorite carnival ride is. Some of you are starting to get it. It's the Ferris wheel. So that's what that indicates. But again, that naming system, you might see it in really old sources, especially if you're reading an old textbook, or maybe sometimes, you know, in like other fields, adjacent fields like biology, they might still use that terminology more commonly than we would. So just to be aware of it. But again, knowing that the charge in parentheses is the important one for you guys to be aware of. So we'll do a couple of examples of that a little bit later on. The other part of ionic compounds that we need to be aware of are what are called polyatomic ions. So this is going to require some memorization. There's a little bit of a systematic, you know, trend to things, but you still have to spend a lot of time kind of learning them. So I have the table reproduced here. It's I don't know if this is the most updated one for your book, but it should have the same information. Where is that? Way down here. Okay, so I put all these different tables in that are relative to nomenclature. So these are the polyatomic ions. You know, some are more common than others, but all of these are fair game. And again, they're groups of more than one atom bonded together that has an overall charge. We actually did an example of that with Lewis structures last time with NO3-, which is called nitrate. So those polyatomic ions can also be found in the formulas of ionic compounds. So you need to be able to know then what is the formula of those ions and their charge. And there are some patterns here that I guess I can quickly point out. This is kind of small for you guys, but it's in the book and you should be able to see it in the notes if you print them out. So NO2-, for example, we have 2 with nitrogen and oxygen. NO2-, which is nitrite, NO3-, which is nitrate. So when you have different numbers of oxygen atoms, the one with fewer is ITE, the one with more is ATE. So look at this table, same with sulfite and sulfate, although this time it's 3 and 4 oxygens. So look at the table and try to, you know, learn some of the patterns. That's helpful instead of just brute force memorizing, but you are going to have to spend some time on that to get familiar with all those different ions. All right, but anyway, the definition of a polyatomic ion is there are groups of covalently bonded atoms. So most of them are groups of nonmetal atoms. There's a couple that have a metal in them as well, but mostly nonmetal atoms. But that group of more than one atom bonded together has an overall charge. So they can be part of an ionic compound. Most of the polyatomic ions that we'll deal with are anions, as it turns out, but there are some cations as well that form this. So the one difference for these is when you're writing the formulas out, you do sometimes need to use parentheses. And that's when there's more than one of those ions in the formula. So if the formula has more than one polyatomic ion, that ion is enclosed in parentheses. And then you have a subscript on the outside that tells you how many of that ion there are. So if we have, for example, sodium with nitrate, so sodium we should know by now is Na+, or if you find it again on the periodic table, it's in the first column, so we'll still predict its charge to be +1. And then if we had it paired up with the nitrate anion, which you will learn very soon if you haven't already, that nitrate is NO3-. So for the polyatomic ions, we need to know both the formula and the charge associated with them. To write the formula for this ionic compound is simple because you just need one cation and one anion to balance the charge, so it will just be fine as NaNO3. But if you have compounds that have more than one polyatomic anion in them, you do need to use parentheses to indicate that you have more than one of those. So if we had calcium with nitrate, calcium would be a 2+ charge, still with the same NO3- anion. In this case, if we want to balance the charges or use the sort of method that we do sometimes with just crossing the charges to make them subscripts, you would have one calcium in the formula, but you need 2 NO3- to balance the charge. So 2+ from the metal, 2 -1s are needed to balance that, so you would write it correctly as NO3-2. All right. So you don't want to write it as without parentheses, because that gets confusing. It's like NO32. Or you don't want to combine things. You don't want to distribute and write it as, you know, CaN2O6. Even though that's the correct chemical formula, it sort of obscures what's actually present in this compound, which is 2 NO3 minus anions. If you group them together like that, then you can't really tell that that's what you have. So both of these are incorrect. You always want to do it with the parentheses like this. You don't need parentheses if there's only one of them, although if you did put the parentheses on there, again, I wouldn't say that that's wrong. It's just not necessary. So parentheses aren't needed, but wouldn't make it wrong either. All right, so let's do some examples that involve transition metals and or polyatomic ions to get the hang of those last couple rules that we just learned. So let's see, we have Fe2O3. So for transition metals, what we have to do is we have to use the formula of the compound to figure out the charge of the metal. Because the key distinction is that the metal can have more than one possible charge. You can't just look it up on the periodic table to figure out what it is. And in this case, the charge is an important part of the name, so we can't just ignore it necessarily either. So if we have Fe2O3, the way we can do this is we have two ions in the formula, iron and oxygen, and we have to kind of work backwards to get the charge of the metal. All right, so we know from the periodic table, if you have oxygen in an ionic compound, oxygen is here, and it's always going to form -2 anions. So just because with a transition metal, that doesn't change. We would predict the charge on oxygen is -2. So that part we can always know from the periodic table. This is a -2 anion. And then we have to figure out what does the charge on the metal have to be able to balance this out. So if we have 3 -2 anions, that's -6 for the overall charge of the anions. So we need +6 on the metals. We have 2 of them, so what does the charge on each metal have to be? +3, good. All right, so by doing that, we have 2 +3s, 3 -2s. That balances out the charge, +6 -6. So we know now from the formula that the metal has a charge of +3, and so the correct name for this would start with the metal name, which is iron. Because it's a transition metal, 3 in parentheses. And so iron 3 oxide is correct. I guess I haven't pointed it out just yet. Fe is here, right in the middle of that first row of the D block. And again, there's no easy way to predict that it would form +2 and +3 cations, but it can form both of those, and even +4 in some cases. So you need to indicate the charge if it's in an ionic compound. So iron 3 oxide would be correct for that. All right, so this is another one here, CuSO4. Again, we don't need the parentheses in SO4, but I do have them here because there's only one of those in the formula. But CuSO4, what you'd have is, for this one, again, it's a transition metal, copper, Cu. It's towards the end of the D block, but it's still in that part of the periodic table. And then you have an anion, SO4. So to be able to do this one, we need to recognize the charge on the anion. Now when they're grouped together like this, that means it's a polyatomic anion. You can't use the periodic table to predict the charges of those, unfortunately, but once you learn all the anions that we have in that table and get familiar with them, it will become second nature if you practice it enough. SO4 is sulfate and it has a 2- charge. Okay, so we know that the charge on our anion is 2-. So if we have a 2- on the anion, then we need to have a 2+ on the metal to balance that. So again, this formula clearly tells us that it's copper 2+ paired with sulfate, because SO4 is always sulfate 2-. There's no variable charges on that. So +2 for the metal, and so when we name this, Cu is copper. We put a 2 in parentheses to indicate that it's in the +2 charge, and then the name of the anion we don't have to change, it's just sulfate. So for polyatomic anions, you don't change the ending at all. It's whatever it is stays the same in the name. So always whatever that full name is, you just give it in the formula and you're done. All right, and then we can work backwards as well. On some level, working backwards with transition metal compounds is easier because the name gives you the charge directly, so all you have to do is just balance them to get the right formula. You don't have to look at the periodic table or do any math to figure out the charges. They're right there for you. So for chromium 3 permanganate, the name tells us directly that it's Cr3+. We do have to know that the symbol for chromium is Cr. And then permanganate, this is one of the polyatomic anions that you'll have to know. If you don't know it yet, that's fine. You still have plenty of time before the exam, but it's going to be MnO4 with a 1- charge. So this is one of the few polyatomic anions that has a metal also at the center, but is so classified as a polyatomic anion altogether. So Cr3+, MnO4-. So when we cross the charges and make them subscripts, we'll just have one metal, Cr, but we need 3 of the MnO4- to balance the +3 charge from the metal, so you'd write it as MnO4 taken 3 times. So parentheses around it with a 3 on the outside. All right, and then the last one here is tin 4 chloride. Did I mess up again? Tin is, yeah, it's too far down the periodic table, so you wouldn't have to know this, but tin is SN. If it was a multiple choice question, that would be obvious from the answer choices that they all have SN in them, so like, okay, that's got to be tin. This is not multiple choice, but if it was multiple choice, you would know that, and again, we would give that to you if you need it. So SN is down here, that's tin. It's a weird symbol for tin, but that's what it is. It's not Ti, which is titanium. So anyway, we have SN, and then that's going to be 4 plus, because for compound, this is not a transition metal, but it's one of our P block metals, and this can be either tin 2 or tin 4, so we indicate it as tin 4, which is 4 plus. And then chloride, we should know from the periodic table, we've seen it already a couple times so far, is Cl with a 1 minus charge, Cl minus, okay? So that's the charge on the anion. So when you're doing these names to formulas, you need to keep in mind the charge on each ion, cation and anion, to be able to balance those out. But again, we can just take the charges and cross them over to make them subscripts, and that gives us SnCl4. All right, so any questions on nomenclature of ionic compounds? All right. The other category of compounds that we'll talk about are binary covalent compounds. There's 2 categories of covalent compounds we'll hold you responsible for. And one of those are called binary covalent compounds, which is a compound that has just 2 nonmetals in the formula. Sometimes more than one of each one, many cases, but only 2 elements in the whole formula, and they're both nonmetals. But for these ones, the difference is that prefixes are needed to indicate how many of each element there are, because they're not forming ions, so you can't just balance the charges and figure out what the formula should be. You have to indicate explicitly how many of each atom is in the formula, because there are often multiple combinations. We talked about the law of multiple proportions like way at the beginning of this course. 2 elements forming 2 different compounds. The example that we gave back then was carbon monoxide CO and carbon dioxide CO2. You need to have those prefixes to indicate how many of each element is in the formula, because that often indicates or does indicate 2 different compounds. So we need these prefixes to indicate how many of each there are. Most of these are familiar to you in other contexts, but we're going to go 1 through 10 is as high as we'll go. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. All right. The only one that's a little bit weird is mono. It's only used in the second element of the formula. So if you have two elements in the formula, and you'll name them in the order that they come in the formula, and the only time you'll use mono is if there's one of the second element. I'm not sure why this was decided to be the case, but the example we gave was carbon dioxide, a molecule you guys are all familiar with. You don't call it monocarbon dioxide, you just call it carbon dioxide. The first element doesn't get the mono if there's just one of them. But then for carbon monoxide, where the second element also has 1 in the formula, you would use the mono on the second element to indicate that. Again, I don't know why that was decided to be the case, but that's how it is. So mono is not used every time, but if it's on the second element, it will be. All right. So where these rules and these prefixes apply are to binary covalent compounds, which I've already mentioned are covalent compounds with 2 and only 2 elements in the formula. Anything that's more complicated than this is going to have a more complicated naming system, so we're not going to go into that, except for one specific class we'll go into a little bit. But binary covalent compounds have 2 and only 2 different elements, and they're both nonmetals if it's a covalent compound, so there's no metals in the formula for these. As we've already talked about, the distinction between ionic and covalent is typically whether there's metals involved. So a metal with a nonmetal is ionic, but 2 nonmetals together is covalent, and then you have to follow these rules for naming them. Now there are rules for the order that the elements come in. I'm going to give them to you just so you know where this comes from, but in reality it's not going to be something you have to really worry about, because on a test question we're either going to give you the name and ask you to find the formula, and you just put the the elements in the formula in the same order as they are in the name, or vice versa. We give you the formula and you just name them in the order that they're in the formula. So that'll always be obvious for you guys because we'll give you one of those two pieces typically. So, but there is a systematic way to do it. So the first element in the name or the formula is the element with a lower group number. That's the one that comes to the left on the further to the left on the periodic table. So that's why when we have, carbon monoxide, when we've been talking about already, you put it carbon first, oxygen second, because carbon is group 4, oxygen is group 6. You don't say oxygen carbide, you say carbon monoxide, or it would be, I guess, if it was opposite, it'd be oxygen monocarbide. But you don't name it like that because you always put the lower group number first. But again, you don't really have to worry about that because it'll be obvious from the context of the question that you're trying to answer. Now, if the two elements are in the same group, we did the Lewis structure of SO3 last time, where both of those are group 6 elements, sulfur and oxygen. In that case, the one with the higher period, which is basically further down the periodic table, that one comes first. That's why it's sulfur first, then oxygen. It was SO3, not O3S. And then when we put the element names when we put the two element names together to make the binary name, you still use the IDE ending on the second element. So even though it's not ionic, we still use that IDE ending for the second one. That's why it's carbon monoxide and not carbon monooxygen. So there's still the IDE ending going on the second one only. Okay? Even though it's not ionic, that's just still the convention. So the key differences between covalent compounds and ionic compounds, there's really two of them here. One is that, as we've already said, you need the prefixes to denote how many of each element you have. So how many of each atom is we need a prefix to tell us that. And the other important thing is that the formula for a covalent compound is not going to be reduced to the smallest ratio. The formula will only have whole numbers in it. It's not going to have fractions or anything, but you don't want to necessarily go to the lowest whole number ratio. You don't need to do that for these. And the reason is that, if we have these two compounds, NO2, which is nitric oxide, and then we have another one, N2O4. So, you might be tempted to say, well, these are the same thing. We can just reduce N2O4 to NO2. But in reality, these are two different compounds. And because they're molecular compounds, the formula tells us how many of each atom is in one molecule of that compound. So NO2 has 1 nitrogen and 2 oxygens bonded together in the molecule. N2O4 has 2 and 4, and they're two different compounds with two different molecular structures. So we don't want to reduce them down. For ionic compounds, we do that because as we'll learn later on in the course, ionic compounds, they're not made up of molecules. They're made up of ions that just repeat over and over and over and over again in all directions. So all you really care about for ionic compounds is the ratio of those two that are in the formula. But for covalent compounds, we do need to know exactly how many of each there are, so we don't reduce them down to their lowest whole number ratios like we do for ionic compounds. All right, so let's just go through some examples then of either formula to name or name to formula. And so if we have SF4, we need to know the names of the two elements. So S is sulfur, and then F is fluorine, but we again change the ending to IDE for the second element. Also, we have a 4 there that tells us that we need a prefix in front of it. So 4, the prefix for 4 is tetra. So we go tetra. Fluorine is the name of the element, but then we change the ending to IDE. So sulfur tetrafluoride would be SF4. The two element names, a prefix. We don't have a mono prefix on sulfur. If it's the first element, you don't use mono. So just sulfur if there's only one for the first one, and then tetrafluoride. All right, if we go to P2O5, 2 phosphoruses is di, 5 oxygen is penta, so those are going to be the two prefixes we need. So P is phosphorus, so the di goes in front of phosphorus, and that comes first because that's the order that they're in the formula. Phosphor, I think that's OUS. I always mess up the spelling of phosphorus. And then it's penta for 5. Now the one subtlety, which I'm not gonna hold you responsible for this. So if but it would just be pentoxide. If the name of the element starts with a vowel, you usually drop the A from the prefix. But again, if you guys mess it up on a test, it's okay. It's not really a spelling test anyway. You'll probably be doing these mostly multiple choice. So, but it would be pentoxide, not pentaoxide. Although you do sometimes see it both ways. So again, it's not one of those things that's really right or wrong either way. Yep.
For these chemical formulas, does like capitalization matter?
When you're writing the name, no. I think for element names, you follow the same rules for capitalization as you would for just any common noun. So they're not proper nouns. So you can, they're lowercase if they're in the middle of a sentence. They would be uppercase if they start a sentence. But it's just grammar rules, not anything about chemistry. That's a good question though. In the formulas, the capitalization matters because the element symbols are always capitalized for the first letter, and if there's 2 letters, the second one is not. But for the name, it doesn't matter. Any other questions? Okay. Now we'll go the opposite way, and I think for binary covalent compounds, in some sense, things are simpler because, everything that we need to name the compound is right in the formula. We don't have to go to the periodic table. We don't have to remember charges or a balanced charge or anything like that. So for nitrogen trichloride, we just need to know that the symbol for nitrogen is N. Chloride comes from chlorine, which is Cl, and then the tri tells us that there's 3 of those. And again, no prefix on the first element tells us that there's 1. So that's just N, and then we have tri, so there's 3 chlorines. So that's, I think, fairly straightforward to go from the name to the formula because it's all right in the name. As long as you learn the prefixes, and as long as you know the element names and symbols reasonably well, you'll be able to get that. Disulfur decafluoride. Di tells us there's 2. Deca is the biggest one we have, which tells us that there's 10. So we'd have 2 sulfurs, S2. Fluoride comes from fluorine, which is F, and that would be 10 of those, so S2F10. So whatever random names we give you, as long as the prefixes are there, it's pretty easy to translate those into subscripts as long as you're familiar with them. All right, any questions on binary covalent compounds? All right, the last nomenclature we have to do to finish out Chapter 3 is, unfortunately, it's probably one of the most annoying ones, but you'll get the hang of it in just a little bit more to it, are naming acids. So we're going to talk about the chemistry of acids later on. I think it's Chapter 5 in this course, I believe, or 6 maybe. I always forget the order of those two. I think it's Chapter 6. But nonetheless, for now we just have to sort of recognize what they are, from their formula, and then be able to name them. So what an acid is it's an anion. So it kind of, in some levels, it resembles an ionic compound because it has an anion in the formula, either something from the right side of the periodic table, like chloride, fluoride, or something like that, or one of the many polyatomic ions that we have, like nitrate, sulfate, and all those. So it has that in the formula, but instead of pairing it with a metal cation, it's paired with hydrogen, which formally is H+ in that case. So it's an anion paired with H+. So if the formula starts with H and has then something after it that looks like an anion, then you can recognize it as an acid. So it'll always have H at the beginning. So there's 2 kinds that we're going to learn about. Binary acids are just 2 elements, so it's just hydrogen with one other element that functions as an anion. So binary acid is H+ with a monoatomic anion. So that means an anion that's just a charged atom, like fluoride, chloride, and so on. So examples of binary acids would be hydrogen with fluoride, HF, hydrogen with chlorine, which is HCl, and again, hydrogen is formally H+, so these are 1- anions, so they just have one H+ paired with them in the formula, or HBr. There's not too many of these, as it turns out. Another common one is hydrogen with sulfur. So sulfur would form a 2- anion. So in that case, you would need 2 hydrogens in the formula to balance the 2- charge. So it's going to be H2S. Sulfur, based on its periodic table location, is 2-, so there's 2 H+ to balance that. It's not really an ionic compound, but it works sort of the same way. Now, the way that we name these is a little bit complicated, but you have a prefix hydro at the beginning, then the root name of the anion, and then at the end of the name you have ic, and then you have a separate word acid. Okay, so that looks like a mouthful, but it's hydro, name of the anion, ic, acid. So if we have HCl, it's a binary acid, H plus with Cl minus, so it starts with hydro. The root name is, this is chlorine, so the root name is just chlor. And we change the ending to IC, so hydrochloric, and then as a separate word, acid. So HCl is hydrochloric acid, HBr is hydrobromic acid, H2S would be hydrosulfuric acid. So anything that, if the name starts with hydro, that tells you that it's a binary acid typically, one that just has hydrogen with another element. All right. The only, and then the other major type that we're going to be responsible for are called oxoacids. So this one you have still H plus in the formula, but it's paired with a polyatomic oxoanion, one of the polyatomic ions that has oxygen in the formula. So like nitrate, sulfate, sulfite, perchlorate, permanganate, all those different oxoanions that we have in that table, which are polyatomic anions that include oxygen in the formula. Hypochlorite, chlorite, chlorate, hypochlorite, or perchlorate, all those different ones, okay? So you have H plus pair with an oxoanion. So you'd have, as an example, HNO3. Nitrate, NO3 minus, pair with H plus. Or if you had sulfate, which is SO4, 2 minus, you would need 2 hydrogens, so it would be H2SO4. All right. And the way that we name these is you take the root name of the anion again. So, you know, nitrate, sulfate, that part of the name comes from the anion, but then you change the ending. So instead of ATE or ITE, which was anions always end with, you change it to either IC or OUS. There's a distinction that I'll give you here in a second, and then you add acid at the end. So if you have an 8 anion, that becomes an ic acid. So 8 changes to IC from the anion, ite changes to OUS. So HNO3, it comes from nitrate, so we replace the ATE with IC, so it becomes nitric, and then you just tack on acid at the end. So HNO3 is nitric acid. H2SO4 comes from sulfate. We don't call it sulfic, we call it sulfuric. So again, there's some subtleties here, but it'll, in the context of a multiple choice question, not be something you have to really worry about. So sulfate becomes sulfuric because it's an ATE anion. But notice no hydro prefix for these. It's just the name of the anion with acid at the end. You don't need hydro in front of it, only for the binary ones. So acids, again, are annoying. We're not going to give you like a ton of nomenclature problems involving acids, but it could come up, and we're going to see acids later on in the course, so we definitely want to be a little bit familiar with them when that time comes. All right, so let's just work through some examples of acids to close out this chapter. So the first one would be named a formula. So we have hydrofluoric acid. All right, so the hydro tells us that it's a binary acid, just 2 elements in the formula, and it should start with H. We don't know how many H's yet. And then fluoric comes from fluorine. And if we go to the periodic table, fluorine is over here. So it would form a 1 minus anion. So we do still need to think about the charges of the anions when we're building up the formulas of acids, because we need enough H plus to balance that charge. So if it's F minus and H plus, we just need 1 of each to balance the charge. It would simply be HF. All right, and when we're writing the formulas for these, we don't have any, we always put the hydrogen first, and we still, you know, use the lowest subscripts and everything like that. So HF is correct here. So we want to put hydrogen first in the formula and then the anion. So that's why HF is correct, but FH is not. So the acid names and formulas always start with hydrogen, the formulas in particular. And we would not want to pick B or C because these are oxoacids. They wouldn't have the hydro prefix in front of them. Not to mention there is no, you know, hypofluorite or fluorate anions to begin with, but nonetheless, if you see hydro, you know that it's not going to have oxygen in the formula. It's not one of those oxoacids. All right, so that's hydrofluoric acid will be HF. And then going the opposite way, H2CrO4. So the formula can sort of give us a little bit of a hint what the charge of the anion is, because there's 2 hydrogens, which means the anion has to be -2. So it's Cr042 minus. But whether we're fully tuned in on what the charge of that is, we need to know the name for this problem. So Cr042 minus is called chromate, one of the rare ones that has a metal in the center for the oxoanions. So as we talked about now, when you have an ATE anion, you change the ATE to an IC in the name of the acid. So it becomes, instead of chromate, it becomes chromic. Then we tack on acid at the end to indicate that it is an acid. So chromic acid is correct, which would be C here. We don't add any prefixes in oxoacids, so no hydro or no per. Only if it's in the name of the anion would we have per there, but it's not in the name of the anion, so we don't put it in. And OUS would be if it was chromite, but this is chromate, so it becomes IC. All right, any questions on acid nomenclature? Again, those are probably the most annoying ones, but they do come up at this time, and there'll be a little bit about those on homework assignments and tests. All right, so that should be, yes, the end of chapter 3. There's all these tables here that I reproduced in case you don't have the textbook, although I think all of you pretty much do. So this is the end of the first exam material. I'll write that in here in case you forget. So everything, as well as the tables, of course, anything in chapter 3, but we're going to now move on to material that is in chapter 4. So I'll write that here to keep that clear as well, okay? So everything now for the rest of today is chapter 4 material. We'll get as far as we can in this. My Fitbit's telling me to walk, and I want to see what time it is. I don't want to walk right now. I'm teaching. All right, so we have about 20 minutes left. So we probably won't get through all of the stuff I had planned today, but we'll continue it next week. All right, so what chapter 4 starts with is we're going to talk in more detail now about mainly covalent compounds and things about their structures, their bonding, a lot of more details that we have not yet talked about in chapter 3, even though we've introduced some of those things at a very basic level. So what we're going to start with in chapter 4 is a method to predict the 3-dimensional shape of molecules. We did Lewis structures Tuesday of this week, just 2 days ago, where we can write these sort of 2-dimensional structures that show how all the atoms are bonding together, show where all the valence electrons are. But that was purely 2-dimensional. I don't know if it was popular when I was a kid, but I don't know if you guys have ever seen this kid's toy called Flat Folk City. Does that ring a bell to anybody? All right, I'm revealing my age again. So anyway, Flat Folk City was like a kid's toy where everything was 2-dimensional, and that's what Lewis structures are. They're just flat representations of molecules. But what we care about also for many areas of chemistry, both related to their physical properties, which we will get into a little bit, but also when you start taking organic chemistry, the shapes of molecules is important for how they react with each other in some cases. The 3-dimensional shape of a molecule is also critical, and so that's what we're going to learn how to do starting today and probably continue it next time because we won't get through it all. So the method we use to do that is called VSEPR. People pronounce it VSEPR, even though the S becomes before the E, but what it stands for is valence shell electron pair repulsion. So in general terms, what is this? What we're going to do is we're going to place the valence electrons around the central atom. So we're going to always have structures here where we have a well-defined central atom and then things that are surrounding that, either other atoms bonded to it or lone pairs. So we're going to take all the valence electrons and place them around the central atom. And this VSEPR is purely a geometric approach. There's not even really a real chemistry basis to it, even though we'll see relations to chemistry later on. But all we're doing is we're placing those electron pairs as far away from each other as possible. Because electrons repel each other, and so we want those electrons to be as far apart as possible so they're not repelling each other to the least extent possible. So however many electron pairs around the central atom, whether they're shared in a bond or a lone pair on the central atom, we want those things to just be spread out as much as possible. That's what VSEPR does for us. So it really relies on sort of geometric arguments. So there's 2 parameters that we can get from this VSEPR approach that are kind of related to each other, but you'll need to be able to sort of understand both of them separately as well. So the first one is called the electron group arrangement. This is going to be the three-dimensional geometric shape that all of the electron groups occupy, both bonding and non-bonding electrons. And as we'll see, there's only really 5 of these that we have to worry about. There's either going to be anywhere from 2 to 6 total electron groups around the central atom, some combination of bonds and lone pairs, and depending on how many of them there are, that's going to define the electron group arrangement, which is the shape that all of those electrons would occupy. The one that is probably in most cases more important or more relevant to chemistry anyway is what's called the molecular shape. So this is the three-dimensional shape that only the bonded atoms occupy. We basically ignore lone pairs. It's not that lone pairs aren't there, and they do affect what the shape is, but what we're defining here is the shape that just the atoms themselves occupy. So in other words, this is sort of what the molecule looks like. Because there are techniques that we can use in chemistry to sort of measure the three-dimensional shape of a molecule. This is not purely hypothetical. This is stuff that can be verified with different experimental techniques, but we don't really see lone pairs when we do that. We just see the atoms. And so this molecular shape just tells us the shape that the atoms are in, ignoring any of the lone pairs that are there and that affect the shape, but are something that we can actually really clearly visualize. So those are the two things. They're related to each other, as we'll see. But basically, to sort of clue you in on what we're going to be doing, the electron group arrangement depends on the total number of electron groups that you have around the central atom, whatever combination of bonds and lone pairs they are. The molecular shape is determined by the specific combination of those you have. How many bonds, how many lone pairs in that combination specifies the molecular shape. So they're related, but a little bit different. Okay, so before we get into the different shapes that we can have, I don't think our textbook actually uses this convention anymore, but I haven't read the textbook in a long time, I confess. But the way that I'm going to categorize things, which I think is still helpful for you guys to do, is with what's called an AXE notation. So it's going to be sort of an abbreviated formula for the molecule that tells us how many each of electron groups we have, and then allows us from that to define what the shape is. So A is basically just a placeholder. It's the central atom. That's always going to just be there. But that's not going to ever really change, or that's not going to affect what our prediction is about the shape. The parts that are important in this notation are the X and the E. So X is going to be an atom that's bonded to the central atom, so one of the outer atoms in the molecule. And E is going to be a lone pair that's on the central atom. Again, for this approach, we're focusing on the central atom and defining everything that is arranged around that. So it's however many bonded atoms there are, how many lone pairs there are. One key thing about X here is it doesn't matter whether it's singly, doubly, or triply bonded. It just counts as one atom if it's bonded to the central atom. So we don't care about the bond order when we're saying how many X's there are. We just care how many things are around the central atom, however they're bonded or arranged. All right, and then in these AXE notation, these M and N are the subscripts that tell you how many of each you have. And it's the combination of those two, M and N, together that define the molecular shape. So there's not infinite possibilities. As we'll see, there's 5 possibilities for electron group arrangement, and then within each of those there's some subcategories for molecular shape, so not too many. And in this approach, X and E are referred to as electron groups. So when we say the electron group arrangement, that's what we're referring to, the total, the arrangement of all of the bonded and non-bonding electrons that surround the central atom. Another important thing to point out is that E is the number of lone pairs. We always pair up the electrons, not the total number of non-bonding electrons, it's the number of pairs. So we'll see that as well. Within this, there's some other terminology that comes out. Again, this is terminology that your book doesn't use, but I will from time to time, which is called steric number. This is the sum of M plus N, the total number of electron groups around the central atom. And this defines the electron group arrangement, so that's why that parameter is important. As I've already mentioned, but I'll point out again here, the bond order between A and X doesn't matter. It can have subtle effects on the shape, but in terms of how we define things using this notation, it's not going to be an issue for us. So A and X, the bond order doesn't matter. Whether it's singly, doubly, or triply bonded, each X counts as just one electron group. And then finally, one other parameter that we're going to define for all of these shapes that we start talking about is what's called the bond angle. This helps us, I guess, quantify things a little bit or understand visually a little bit what's going on. It's the angle between two bonded atoms with the central atom as the vertex. All right, so as an example, if we had water, H2O, what we will learn here in a little bit is that water has this sort of bent geometry. The hydrogens are not completely opposite each other, they're bent a little bit. And we can predict that with VSEPR. And this angle here would be the bond angle for water. Many molecules that are more complicated have more than one bond angle, but there's only one here because there's only 3 atoms. And we would indicate that or abbreviate that as angle HOH is sort of an abbreviation for that. The angle between the two hydrogens with the oxygen at the center. And that bond angle is going to be characteristic of the electron group arrangement and the geometry that we're talking about. So the key to doing this then is, if it's not obvious already, is you have to first draw a reasonably good Lewis structure. You have to have your center atom bonded to the correct number of outer atoms with the correct number of lone pairs as well. So you have to produce a Lewis structure first, and then once you know how many atoms are bonded to the central atom, that part's easy because that comes from the formula of the compound. But then you also have to know how many lone pairs there are, which requires you to draw a decent Lewis structure. Once you have both of those pieces together, then you can go forward and translate that into a 3-dimensional geometry. So first we're going to do it in abstract before we start sort of talking about real molecules. So for the rest of today, we're going to just march through the different possibilities and see what they look like. We'll continue next time if we don't finish. But we'll start with the smallest ones, which are 2 electron groups. So I highly encourage you to use this simulation here that's in the notes. And I'm going to actually use it today as I teach this stuff, because it's a really good way of visualizing these shapes in 3 dimensions, better than you can do by just drawing them, or better than I can do certainly by drawing them. And then we can go through them. So that's what I have opened up here. So it has, you can either do it with models or real molecules. Today we're going to be doing sort of just, in general form with models. So if we start with 2 electron groups, in this case shown as 2 atoms bonded to it, this one I think is fairly intuitive. VSEPR wants us to put those things as far away from each other as possible. So if there's 2 of them, put them 180 degrees apart. That's as far away from each other as they can be. So when you have 2 electron groups, they're going to arrange themselves 180 degrees apart in what's called a linear geometry. All right. So AX2 would be the notation where both electron groups are atoms bonded to the center atom. So it would be a linear geometry to put those as far away as possible. And the bond angle is exactly 180 degrees. All right. And then one thing that I'm going to point out as we go through these is if you have no lone pairs on the center atom, so if it's just AX2 with either no E's indicated, or you could write it as E0 also. You could write it as AX2 E0 also. But basically if there's no lone pairs in the center atom, then the electron group arrangement and the molecular geometry are the same. So for 2 electron groups, the electron group arrangement is always going to be linear. And then when there's no lone pairs, the molecular geometry is also the same as that. So for any of the structures where there's no lone pairs on the central atom, the electron group arrangement and the molecular geometry are the same thing. So linear for both in this case. Now with 2 electron groups, we can also have an AXE arrangement. So I'll give examples of these, and then we'll do examples later on. So an example of AX2 is CO2. Now we can also have AXE. So for AXE, what you're doing when you introduce lone pairs is you're starting with the same electron group arrangement. So there's one X and one E. There's still 2 total electron groups. So they have to go 180 degrees apart. But then you need to introduce a lone pair into one of those positions. Now both of these positions are the same. They're on opposite sides of the central atom. So it doesn't matter where we put the lone pair. We can put it over here. X goes over there. This one is trivial because if you have 2 atoms in the formula, it has to be linear. I'm not a wizard in geometry, but I can't think of a way that you can arrange 2 things in shape in space that aren't in a straight line. Or so anyway, if there's only 2 atoms in the formula, it has to be linear. AXE, AXE2, AXE, whatever. If there's only 2 atoms in the formula, it's going to be linear. So we have a simulation of that. So if we replace one atom with a lone pair, that's AXE. So you can see that the atom and the lone pair are still 180 degrees apart, but the molecular geometry is just the 2 atoms, which has to be linear because there's only 2 of them. Okay. All right. So that's going to be also linear. There's no bond angle in this case because there's only 2 atoms. You can't define a bond angle for only 2 atoms, so not applicable. And an easy thing to realize when we're doing molecular shapes is that all diatomic molecules, so any compound that only has 2 atoms in the formula, whether it's 2 of the same atom like O2 or 2 different atoms like CO, if there's only 2 atoms in the formula, it has to be linear. There's no other way around it. So all diatomic molecules have a linear geometry. So for those, you don't necessarily have to go through and do all the AXE and all the different notations and things. It's going to be linear without thought. All right, so that's 2 electron groups, which are obviously the easiest ones because there's only 2 of them. Let's step it up now to 3 electron groups. So if we have 3 electron groups, you don't have to be really good at geometry to figure this one out. So if we have 3 things around a central atom and we want them to be as far apart from each other, anybody have a thought on how we might do that? A triangle, right? So we put them as an equilateral 120 degree triangle, and that puts them as far away. So for 3 electron groups, we're still only in 2 dimensions here. So we call that electron group arrangement trigonal planar. So anytime there's 3 electron groups, that's going to be the electron group arrangement. So for AX3, let's look at the simulator first and see that our reasoning was correct. Sorry, I went to the... All right, so if we go to 3 electron groups, we see that they're going to arrange themselves into a triangle like that. So with AX3, that would be a trigonal planar geometry also, where there's no lone pairs. The geometry and electron group arrangement have the same name, and they're really the same thing. We can see if we look at the side view that it is, sometimes this thing's hard to rotate, but it is flat. So it's totally flat trigonal planar structure. Okay, so that's what AX3 would look like. So we have central atom, and then the 3 things are going to be arranged in a triangle. We call this trigonal planar, and again, because there's no lone pairs, AX3 has the same electron group arrangement and geometry. And the bond angles, as we already said, are exactly equal to 120 degrees. All right, so that's going to be AX3. If we go to AX2E, this one still has 3 total electron groups, but this time one of those 3 is a lone pair, so it's 2 X's and an E. So because there's 3 total, it's still going to be trigonal planar arrangement, but now one of those 3 positions has to be a lone pair. Now all 3 of these positions are equivalent. They're all 120 degrees apart from the rest. So you can pick any of the 3 and make it the lone pair. I'll pick this one just to make the geometry a little bit easier to visualize. And so this is going to be AX2E. Now when we're naming the molecular geometry, though, we only care about the atoms in the formula, the A and the 2 X's. We don't care about all 3 things. So it's no longer called trigonal planar for the molecular geometry. And this one has a pretty simple name. It's just called bent. Sometimes you'll see V-shaped, but bent is probably more common. And again, as an aside and as a pattern we're going to want to recognize as we do this, if you have 3 atoms in the formula, AX2, E whatever, your only 2 options are bent and linear. The 2 atoms around the center atom are either like this, bent, or they're like this, straight across from each other. In this case, because of the lone pair being in that 3rd position, they have to be bent. And then in terms of the bond angles for this, they're going to still be close to 120 degrees because it comes from the trigonal planar electron group arrangement. But this lone pair here is more strongly repelling than a bonded pair. It occupies more space. So it's going to push down a little bit on those. And it's actually going to compress the bond angles a little bit. So we can't say exactly what they are. They're not going to be that different than 120, but they're going to be like a little bit less than 120 degrees. All right, so that's going to be what we see for bent. Some real examples of this, a lot of those boron compounds that have incomplete octets, like BF3 would be AX3. An example of this would be SO2. So there's real molecules that pretty much fit into all of these shapes. These aren't just imaginary things. All right, so when you have AX2E, it's going to go bent, and the bond angle is going to be a little bit less than 120, but not that far, maybe just a couple degrees. It depends on what A and X are, how far that deviates, but it's not going to be very, very big deviation. So when you're answering like a test question, you would put less than 120 degrees, but you couldn't be more specific than that. All right, so that's 3 electron groups. Now when we go to 4 electron groups, which we have time for now, this is where we have to start thinking in 3 dimensions. And it's not, especially this one, I would say, is not particularly intuitive how we arrange things. It's unless you're really good at 3-dimensional geometry, you're not going to get this. So let's look at the simulator to see what this one looks like. So again, that's AX2E. I didn't show that one yet, but that's AX2E where they're bent, still in a trigonal planar. But now if we go to 4 total electron groups, so this one is called tetrahedral, and it's hard to visualize, but there's sort of 2 ways to visualize it. One is it's sort of, 2 bent, I can't really use my pointer very well in here, unfortunately, but it's like 2 bent fragments that are arranged 90 degrees apart, so one there, one there. Or the other way to sort of think about this is it's kind of like a 3-legged piano stool. So it has like, 3 legs on the bottom and then one pointing up top. But it's called tetrahedral, and now it is 3-dimensional, as you can see. They're no longer flat. They're no longer in the same plane. All right, so this one's called tetrahedral. And tetrahedral is sort of a nice name for this because tetra tells us 4. Although it's not called tetrahedral because there's 4 electron groups. It's called tetrahedral because if you draw a solid through those points, it has 4 triangular sides. That's where the tetrahedral comes from. But nonetheless, it helps us remember that there's 4 electron groups that give a tetrahedral arrangement. Now, in terms of how we would draw this in 2 dimensions, it's not trivial to do because you have to. So in chemistry, the way we do this is for tetrahedral, there's going to be 3 atoms that are all in the same plane, so we just draw regular, straight lines for those. There's also going to be 1 atom that comes out towards you and 1 atom that goes back away from you in 3 dimensions, which is hard to draw. So the way we indicate that is with a wedge for the one that's coming out towards you and a dashed wedge for the one that's going back away from you. And so basically this one, I didn't do a perfect job of drawing it, but essentially I'll try to give it the same orientation on the simulator. I drew it kind of like this, where you have the 2 white atoms on the left and the central atom are all in the same plane, and then you have the one in the front that's coming towards you, where the little hand is right now, if you can see that, and then the one in the back that goes away from you. And you draw that with a solid wedge, that with a dashed wedge, to indicate that they're pointing into and out of the plane of the page. So that's just how we draw it. The main thing for you guys to be able to do is name the geometry. We can't have you draw on blackboard anyway. So for AX4, we call this tetrahedral, and that's also the name of the molecular geometry when there's no lone pairs. And the bond angle is not intuitive at all, so it's just a number that you have to become familiar with, which is 109.5 degrees. And a lot of carbon compounds have tetrahedral geometry, so CH4, methane, would be an AX4 molecule. Okay. And again, you can't just tell from the formula, you have to know how many lone pairs there are, but CH4 would have 0 lone pairs, so it would be AX4 with no E's. If we go to AX3E, we're going to replace one of these atoms with a lone pair. And again, in this geometry, in most geometries, all of these positions are equal. They're all 109.5 degrees apart. So it doesn't matter where we put the lone pair. It can go in any of these 4 positions. So I don't know what the computer is going to do, but we'll take one of those out and put a lone pair. So it kind of twisted things around. But again, for easier visualization, I think putting it at the top is helpful. And so what you get for this, which is AX3E, is going to be, now it's just, you know, sort of like a 3-legged stool with nothing coming up. So it's just a pyramid. So it's a pyramid with a triangular base. So 3 white atoms make a triangle at the bottom, and then you have the center atom forming the cap of the pyramid. So what we call that is trigonal pyramidal. So when you have AX3E, we start with a tetrahedral electron group arrangement. So same electron group arrangement for all 4 things, but now one of those is a lone pair, goes in any of those positions. We put it up there to make it easier to see, and this we call trigonal pyramidal. And so again, the x's make sort of a triangle, even though it's hard to draw in 2 dimensions, and then the A sort of caps that pyramid. All right, so it's easier to see in the simulator. Obviously, that was not helpful at all. But anyway, it's trigonal pyramidal with 3 x's at the bottom, and then A caps it. And same argument as before, the bond angles here, because of this repulsion from the lone pair pushing down on everything, that's going to compress them a little bit. It's almost like starting to fold an umbrella, although not very much, but a little bit. And so the bond angles here are going to be a little bit less than 109.5. So an example of this is ammonia, NH3, where the nitrogen, in addition to the 3 hydrogens, has a lone pair on it. So that's why it gets this AX3E arrangement. And the bond angles in NH3 are like 107. So as I said, it's a small difference. It's like 2 degrees or so difference between the ideal 109.5 when you have a lone pair. So it's a little bit different, but you would still predict close to 109.5. That's the best we can do. So that's trigonal pyramidal. And then the last one we'll do today, and we'll pick up the other 2 next time so we don't have to rush, is the last combination with 4 electron groups. So another possibility with 4 electron groups is that you have 2 of each, 2 bonded atoms and 2 lone pairs. And so if we do that, we're going to replace one more with a lone pair. And we're left with only 3 atoms. And as we said, 3 atoms are either linear or bent. And as you can see here, because this came from a tetrahedral arrangement with 109.5 degree bond angles, they're going to be bent in this case as well. 3 atoms in the formula have to be linear or bent. Here they're clearly bent. So for AX2E2, we have the 4 electron groups still arranged in a tetrahedron, but now 2 of them are lone pairs. It doesn't matter which 2, they're all still 109.5 degrees apart, and so that would be one way of drawing it. Or more clearly, you put the 2 x's and the A in the same plane, and then you would have a lone pair coming in and out that you don't really see. But the geometry of the 3 atoms is clearly bent. So this is another example of bent, sometimes called V-shaped, but not more often called bent. And the bond angle here is also going to be close to 109.5 because it comes from the tetrahedral electron group arrangement, but it's going to be a little bit less. And a little bit more or less because there's now 2 lone pairs pushing down. So an example of this is one that we drew at the very beginning, which is water, H2O. So H2O has an AX2E2. If you draw the Lewis structure of H2O, you'd have 2 lone pairs on oxygen to complete the octet. So you'd have the 2 hydrogens and 2 lone pairs, making it AX2E2. And I think the bond angle for water, I don't remember it exactly off the top of my head, but I think it's like closer to like 105. So if you have a second lone pair, it compresses it a little bit more. So, NH3 is 107 with 1 lone pair. With the second lone pair, it goes down to like 105. But it's only a few degrees difference. It's not a huge effect of those lone pairs. All right, so we'll continue with 5 and 6 electron groups next time, and then start talking about other things we can learn if we know the molecular shape. So we'll cover that next week.
Yeah.